So, thanks for being here, although the rain is not so nice, so we're lucky with the last 3 days. But I think we can continue with a good day today, tutorials. So, my name is Sebastian Schmidt. I'm from Heidelberg University of the Electronic Visions Group. And together with Eric Müller, we will do the tutorials in the afternoon and also in the morning. And you will be able to run experiments on both generations of the BrainScaleS platform with the Wafer-scale module and the prototype. So although it looks like the same size here on the picture, this is like super tiny, this is like super large. Of course, second generation will hopefully one day also be on the same scale as the generation 1. But to put these things in context, let me quickly remind you of the basic architecture that both of these systems follow, which is physical modeling. This means that for every synapse and for every neuron, there is a physical circuit on the chip. So it's like a Petri dish, although it's a silicon wafer, both round at least. What we try to do is model closely biological principles. So for example, when you take a biological neuron, some of these can be pretty well modeled by the so-called adaptive exponential integrate and fire model, which is by itself a set of differential equations that you can see here on top. Yeah. So what do you do when you have a set of differential equations, but you want to do a physical model system? Actually, it's not so difficult. Let's say we only have an integrate and fire model, then it's really simple. What you do is you need to devise a circuit which looks like this. Yeah? So all your membrane capacitance is just a capacitor. Your leak potential is just a voltage source. Your leak term, which determines your membrane time constant, is more or less a resistor. And then when you put in current here, synaptic activity, you just compare the value of the capacitor with a threshold. You elicit a spike and communicate it to the next neuron. So of course, things get more hairy when you have an adaptive exponential integrated fire neuron, and you really want to put it in silicon. And this is what you see on top here. Yeah, so that would make a good rug, but it is actually the layout of one of these neurons. Yeah, so you have a lot of layers and more transistors for all these terms, but it can be done, and we've done that. And so on this big wafer, we have about 200,000 of these neuron circuits and 400 more synapses. So what happens when you do these circuits in silicon? It is that capacitances in CMOS process, this is what we use, are very small, and resistance as well. So conductances are large. And when you do the math, you see that this gives you a very small time constant just by itself, if you take a look at this RC circuit. And this means that these dynamics here evolve about 1,000 to 10,000 times faster with respect to biology. So for free, we get an acceleration factor. Of course, communication with the outside world needs to be on the same scale. So this is what makes it difficult. It's easy to get it fast, but then it's not so easy to put everything together and let it communicate with each other. And then when you do everything, then you can see some firing patterns for some current input. And this very well matches what you expect from the differential equations, although not perfectly, and this you will see in the tutorials. So what is BrainScaleS-1 system? This is the machine room in Heidelberg. You will run your experiments on one of these modules remotely. And although there's a big machinery, we try to make it as easy as possible. And every experiment is formulated in the Pine language, which is geared towards neuroscience. So it's expressed in terms of populations and projections between them. But also there's low-level access to hardware parameters if needed. Yeah? So you get both views. You get a very high-level view, but you then can go down to the individual circuit parameters if needed. So this is a visualization of the wafer. This is about like 20 centimeters in size. It had 400 of these chips, each having about 500 neurons. And here we tried one of our commissioning experiments. You start at the very top, building a Synfire chain, then you go around the wafer, do some forward inhibition to make a controlled propagation of information. And here you see that this volley of spikes traverses through the wafer. And this is about 13,000 neurons and about 200,000 synapses. And I want to highlight a publication that we did a while ago as preparation for these studies. This is our so-called compensation paper, because this is analog circuits and you get some variation and you need to compensate for maybe parameters that are not in the range of the ideal model. And we did a lot of studies there to make theoretical models functionally principal on the substrate. Another example is when you have a balanced random network. So former example was to have a very large fraction of the wafer workable, and here we try to make it as dense as possible. This is an experiment of 3,000 neurons. It has about 700,000 synapses. What we do is we feed every neuron with external processors with about 50 Hertz biological rate. But as explained, you need to take into account the acceleration factor. And this means you have about 400 megahertz wall clock rate that we feed in from the outside. Another example that we did is when we want to really make use of the spike timing. There's a theory by Mostafa, supervised learning based on temporal coding in spiking neural networks. And here we did a proof of concept implementation that learns to recognize patterns using a time to first spike coding. So you have a layered network, and at the end you read out which of the label neurons spikes first. And this is your information. And for that you can get a very energy efficient and fast approach to feature detection. So you do not have to integrate a rate, but you say, okay, this neuron spiked first. This is the result of the classification. Here's some reduced MNIST, and you see that the confusion matrix is very good. Of course, we want to scale this up. This is only proof of concept implementation. Okay, so I will hand over to Eric.
Okay, so we will have basically a tutorial that is split in two parts. The first part is the large-scale BrainScaleS-1 system, and we will also demonstrate the BrainScaleS-2 system. We also have one with us. It was being shown at the poster sessions. We will also bring it to the demo session. Now, regarding the BrainScaleS-2 system, you heard maybe the talk of Johannes Schemmer. The basics of the system are the same as in the BrainScaleS-1 case, so analog neurons. A certain differential equation for the neuron is modeled. So essentially, it's very similar to the BrainScaleS-1 system, with the exception that it has a programmable embedded processor. And the second fact is that it's currently still a small prototype chip. We have taped out a larger chip, which will be in our labs very soon. So yes, so this will change very soon. So regarding the embedded processor, this processor was, its main application, at least at the beginning, that was my impression, was basically targeting for programmable plasticity. So you have capabilities on the chip to observe certain state variables in your system. So for example, you can measure the accumulated correlation within the synapses, which happens in a massive parallel fashion. So you have access to those observables. You can access the neuron spike count, so the neurons themselves count their outgoing spikes. In principle, you can also access individual spikes. Obviously, this is then you get a scaling problem, because you have to receive quite a lot of them. So usually you don't want to look at individual spikes. Then you have quite some controllables. So in principle, the full system can be configured from the embedded processor. You have access to the weight matrix, you have access to neuron parameters, and other digital parts of the chip, and also some analog parameters. The main purpose in that regard is to implement different kinds of, for example, STDP, structure plasticity, homeostasis. You have seen examples for this in the talk by Johannes Schemmel and at the poster/demo booth. But the embedded processor can be also used for other tasks. So we have a paper published where we use the embedded processor to do both programmable plasticity and a simulation of a virtual environment. So you can run different kinds of code on the processor and interface the analog neuromorphic part with your virtual environment or what you want to do on the system. Maybe next slide. Thanks. There are examples now. So structure plasticity, it's basically on, it was what we have shown on our slides. There are some YouTube videos on our YouTube channel. So if you look up the BrainScaleS YouTube channel, you can also have a detailed look at those videos. Okay, and maybe regarding the...
Okay, so as said, you will have the chance to do both. So both the morning session and the afternoon session is the same, and it's split in two parts. One part for the BrainScale system, one part for the prototype system. So you have access to play with both. And in the BrainScale's hand-on session, you will remotely access, as I said, one wafer module here of the machine room in Heidelberg via a Jupyter notebook. So you just need a browser. You will define spiking neural networks using the Python-based Pine API. You will visualize the generated hardware configuration, and then you will run experiments and analyze the results. And then from there on, you can basically do whatever you like. So there's template code that you can then adapt to your liking.
And regarding the BrainScaleS-2 hands-on tutorial, this will always happen in the second part of the individual 2 slots, because the first part basically also gives you an introduction on how to configure our systems if you use the full automatic software stack. For the BrainScaleS-2 system, in the hands-on tutorial, we will use a lower level software stack where you can really play around with the individual bits that you can set on the chip. You will also work with the embedded processor, and you will see how to write code for the embedded processor, how to upload it to the system, and how to build an experiment protocol on a low-level basis. So you will really see the low-level configuration and runtime API. Okay, and I think that's it regarding the BrainScale systems.